I guess you can hear me. I will talk about decidability. So I want to talk about Rice's theorem, but we'll just give a introduction. So actually, Rice's theorem is used for decidability, that is to decide something. So first we have to see what is the something which we have to decide. So we have a set of strings which we call a language. So one example is this L1, which is having just 5 strings. So, and now we have L2, which is having infinite strings. So our decidability question is whether a given string belongs to either L1 or L2. So how will we do this? So I'm not going to say how we do this. I suppose you already know that for L1, we can make a DFA, which will have a finite state corresponding to each of the 5 strings. And like this, for any finite language, we can always have a DFA. Now for L2, here we have an infinite set of strings, but still we can have a regular expression for L2, and so a DFA for L2. So we know a way to decide L1 and L2. And similarly for any finite language or a regular language. And for both these finite and regular languages, we can have a DFA. And for context-free languages, DFA is not enough. And we need a PDA, that is a push-down automata. Now for context-sensitive languages, we need an LBA, that is linear bounded automata. Then for some languages which are not context-sensitive, it can be regular recursive languages, and we need a Turing machine for it. Now, even there are some languages which are outside recursive languages, and they are recursively enumerable languages. Again, we just need a Turing machine for these languages, but the thing is, these Turing machines may not always hold. More of this later, but there are some languages which are not even recursively enumerable. No machine can determine membership. Okay, now I guess most of you will know about Turing machines, but I don't think anyone will have seen an actual Turing machine. But we all have seen computer, and a Turing machine is almost equivalent to a computer. That is, whatever we can do in a computer, we can do it on a Turing machine. Sorry. So I got a call. Yeah, but there is a small difference in a normal computer and a Turing machine. That is, in a Turing machine, we talk about an infinite tape, but which is equivalent to a memory on a computer. All the computers have a finite memory. That will be like 8 GB or 16 GB or 32 GB, but we practically cannot have an infinite memory. So that makes it to a normal computer mostly equivalent to a linear bounded automata. For our discussion, we can just consider Turing machine equivalent to a normal computer. So to decide a decidability question, we can see 2 examples. One is given an input program, that is, we are considering a computer, not a Turing machine. So I am asking you to write a C program which actually takes 2 inputs. One is another an executable and an input word, and you have to decide if when run will halt on this given input. Now the Second problem is almost the same. Question just reverses. That is, instead of saying whether it stops on the given input, now you have to say whether it do not stop on this given input. So I don't think normally anyone will ask this question whether, I mean, you will always hear whether it stops. No one usually asks whether it does not stop, because if you say an answer to whether it stops, it always implies whether it do not stop also. But that is how I mean uh, sorry yeah, but there is a reason why this is told like this, which we will see soon. Yeah, so now normally if you are familiar with C program, what you can simply do is just write this line, that is, and give the input exe as the first argument and the input word as the second argument. Now actually the given program is running on the system, and if it holds for that input, we know whether we have the answer yes. Otherwise we can say no, but the program is still running, so we will have to wait for the program to stop, and it is not going to stop because that is how the executable is written. Maybe it is just having an infinite loop. So if we do like this, we will never say no, it will simply loop forever. So that is, so now we have a way to always say yes whenever the given input program holds for the input word. And unfortunately, if the given input program is not halting, we do not have any way of saying no. Actually, what you saw now is the exact halting problem, which is given in any TOC book. And this problem is the well-known undecidable problem. Is we do not have a way to say yes for all the yes or no for all the inputs. So that is why actually we separated this problem into two, that is 1 and 2, because even though we cannot say yes or no for all the inputs, we can always say yes for all the inputs. The answer is yes. So this might be confusing for you, but just think like this. For any decidable problem, there is only two answers, whether it is yes or no. And this yes or no depends entirely on how the problem is stated. So the best example is this only, because whenever problem 1 says yes, problem 2 says no. That is for a given input. So this is just because how 1 and 2 are like complementary problems. So whenever we can say yes for the yes case, that is for of input, we have a way to say yes. So this forms a different class of languages, which are called recursively enumerable languages, which we saw earlier. That is language number 6 here. So this is just theoretical definition. It is kind of, we have a set of undecidable languages, and from that set we are saying some of those languages are undecidable but are still recursively enumerable. But recursively enumerable also includes all the languages which are recursive, because it is just a superset of recursive languages. Just that it also includes some undecidable languages. And One example is our halting problem only. That is problem number 1. Problem number 2 is not actually halting problem, but it's complement. Problem number 2 is stated, we can always say no for all the no instance, but we cannot say yes for all the yes instance. So unfortunately or fortunately, we do not have any separate name for those set of languages where we can always say no for all the no cases. So we will simply say that language number 2 is not recursively enumerable. Language recursively enumerable but not recursive. Okay. So, okay, now we can just have a break. I want to see how the discussion went. So I'm just stopping the discussion for now.